So as I expected, the mean was higher on the second midterm than it was on the first one. I thought it was going to be even higher than what it was, but it's about 17, I think, close to 17. Whereas the mean on the first exam was around 15. So there were more scores in the 20s this time than on the first exam. Okay, but we need to keep going on here with the lectures, and if you recall, what we have been doing is combining for this last lecture, this last few lectures, combining our basic flows to produce yet some additional flows. So last time we talked about the half body, right? And then at the very end of the lecture, I ask you, how do I make this half body be actually a whole body with a front and a back? And if you remember, the way we created this half body was by superimposing a source at the origin. So there is a source right here at the original coordinates, and we superimpose onto that a uniform flow. And we found that there was this streamline that I have now drawn in brown. And if we use that streamline to define the surface of an object, then that's what our half body is. So I ask you, how, if I wanted to actually make this a complete body with a front and a back, what should I do? I would add a sink somewhere back here. And if I do that, if I add the sink back here, then it will essentially produce a symmetric object that is also closed with a round trailing edge that is called a Rankine oval. So if I were to do that and close it, what I get is something that is called a Rankine oval. So it's a source at the origin, for example, like we have here, and then a sink somewhere down here along the x-axis, the positive x-axis, and then a uniform flow superimposed to that. But I won't go into the details of the Rankine oval. Instead, what I'm going to do is show you how to create another important superimposed flow, which has very many practical applications in aerodynamics. And the way we're going to do that is we're going to start with the doublet. And you've seen this figure already before. The doublet, remember, we obtained by taking a source and a sink and putting them together at the center of the original coordinates, but we had to also increase the strength of each so that when they meet at the center, they don't cancel out, and that's how we got the doublet. And then I also told you that the doublet, in fact, represents the flow produced by a moving cylinder. So if I have a cylinder here that is moving from right to left with some velocity, then this would be the unsteady picture of what the streamlines would look like at the time the cylinder is right at that position. So if the cylinder were moving from right to left, then you will essentially see that picture at each instance. So as it moves, it just produces that pattern as it passes by. So it's like we take a photograph at the time it happens to be there, and that's the flow pattern. And I told you that it makes sense intuitively that it should look like this, because as the cylinder is moving to the left, it's pushing the fluid ahead of it, so it's pushing it out of the way. And then, of course, in the back, as the cylinder again is moving, it brings fluid in from the back, because it's leaving a void space as it moves to the left. So that's what it is, and so that's represented by the doublet. So the doublet has a real physical interpretation. So what we're going to do next to create a new combination is similar to what we did with the source. So suppose I take that doublet, and there is the doublet. In this case, I have taken out the cylinder itself. So we can see the full doublet flow field. And then what I'm going to do is superimpose a uniform flow. So I'll take my doublet flow field and superimpose a uniform flow and find out what's going to happen. So again, for comparison, think of the half body. What we did is we took a source and superimposed a uniform flow. And the first thing that we did was to see whether there were any stagnation points in the flow field, and we're going to do exactly the same thing here. So I'm going to ask you, do you think there will be a stagnation point somewhere in this flow field when I combine the two? Yes, and where? On the x-axis again is in fact the same qualitative description. If I look at, there must be a point somewhere along this negative x-axis that there has to be a stagnation point because the velocities are in opposite directions. The one due to the doublet is to the left, and the one due to the uniform flow is to the right. So when they have exactly the same magnitude, they will cancel out. So I would expect that there will be a stagnation point there, just like it happened for the half body. But do you think in this case there might be another one? Could there be another stagnation point? Just from a qualitative look of the streamlines that you have there. On the positive x-axis, because this time, as opposed to what happened with the source, this time on the positive x-axis we have the same situation because the uniform flow is all the way to the right anywhere, and here somewhere I also have opposite flow directions. Right? The doublet is making the fluid go from right to left, and the uniform flow is going from left to right. So I expect there will be then another stagnation point back there. So let's say we don't know exactly where they are, but let's say that they are here and here. So what did we do after that? Can we find, for example, where they are? And the answer is yes, we can find where the stagnation points will be if we simply go through the mathematics of the combination. So again, what we're doing, let me leave that there, is we are superimposing a uniform flow and a doublet. And remember, because the stream function satisfies Laplace's equation, I can superimpose the two. It's a solution of a linear equation. So here it is, the stream function for a uniform flow. I'm going to add it to the stream function for a doublet, and if I go back and look what they are and put them here, then the stream function for uniform flow, remember, it was the velocity of the uniform flow, u naught times y, and the doublet was negative k sine theta over r. So there I am adding them up, except that if I want to look at the details of what's going on, I rather write them both in cylindrical coordinates. So the next step is just to take the y from the uniform flow and write it as r sine theta. So I write it like that. And so that's my stream function. And of course, because I see that the sine theta appears on both sides, I can conveniently factor it out. In fact, I will also factor out an r, even though there is not an r multiplying both sides, but I'll just fix that by putting this r square underneath the k. So if I factor out r sine theta, then what I have is in the parentheses u naught and then minus k over r squared. And that's my stream function, my combined stream function. So there, in that expression, I can already see some of the features of the flow. For example, remember, what is the x-axis in cylindrical coordinates? The x-axis. I should probably, in case you don't remember, I will draw here the cylindrical coordinates. Remember, it's to a certain point here, it'll be r, and this will be theta. You still see that? So what is the x-axis? Let's say the positive x-axis.
0.
Theta equals 0, right? Theta equals 0 is the positive x-axis. And the negative x-axis is theta equals pi. So in either case, if theta is equal to 0 or theta is equal to pi, the sine of theta is 0. So we, just from looking at this expression, can conclude that the whole x-axis is a streamline, because it has the same value of psi, which in fact is 0. Because if I put theta equals 0 or theta equals pi, I cover the entire x-axis and I get psi equals 0. So we just figured out that this line is psi equals 0. So therefore, my two stagnation points are on the streamline corresponding to psi equal to 0. But what happens is that this expression here has another way to be equal to 0. Right? I can also, like I said, I can pick theta equals 0 or theta equals pi, and that gives me 0. But I can also make the parenthesis 0. And I also get psi equals 0. So if the parenthesis is 0, what do I get? If the parenthesis is 0, what shape do I get? I said u naught minus k over r squared is equal to 0. Solve for r. And I get r is the square root of k over u naught, which is a constant. Right? So the square root of k over u naught is a constant. So I'm getting that for r equals to a constant, right, psi is also equal to 0. But r equals to a constant defines a circle of radius, in fact, square root of k over u naught. So in fact, that must be the distance from the origin to either of these points, because it has to coincide with that circle. So I can then say, from what I just found out, I can draw this. That I have just found that the streamline psi equals to 0. See if I can keep that there. The streamline psi equals to 0 corresponds either to the x-axis or to this circle. So all those two figures, the x-axis and the circle, have psi equals to 0. So there is a streamline, in fact, that looks like a circle. All right? So if I continue with this analysis, then this is what we had already found out. R sine theta is 0 if sine of theta is 0, which is the x-axis. So I have the two places, the circle and the x-axis, as the places where the psi is equal to 0. So because I can always choose a streamline to represent a surface, then I can say, well, I'm going to take that circle to be a solid surface. And if that circle is a solid surface, then what's going on here? Well, what is going on here is that I am getting the picture of a uniform flow past a circular cylinder. Right? So, but let's see exactly if that is true by looking at some additional details. So we keep going with this analysis. Here's the same picture, but a little smaller. There is the psi equals 0 horizontal axis and the circle. Let's find the velocity. Since we have the stream function, I can get the velocity out of the stream function. And remember, the expressions for the velocity in cylindrical coordinates are these ones that you have here on the left. So v sub r is 1 over r d psi d theta, and v theta is minus d psi dr. So I simply take my stream function up here, right here, and differentiate it with respect to theta and differentiate it with respect to r to get these expressions. So let's just quickly, you can write it down and then verify the algebra later. But if I do that, if I take d psi d theta divided by r, I get this. I get u naught, and then a factor of parentheses 1 minus a squared over r squared, and then times cosine theta. And for v theta, I get minus u naught, parentheses 1 plus a squared over r squared times sine theta. Those are then the components of the velocity field for this combination, doublet plus uniform flow, the velocity field anywhere, at any point. But of course, I am more interested to find out what the velocity happens to be on the circle itself. So on the circle itself. So if I do that, let's move this up a little bit and see what happens on the circle when r is equal to a. See, what I did is I called the square root of k over u naught a. I did that up here, just so that I can simplify the writing. So what are the values of the velocities at r equals a? So let's check quickly. So we see v sub r, if r is equal to a, is 0. So this goes to 0. And if r is equal to a in the v theta expression, then this is just 2. So this is minus 2 u naught sine theta. So we can write that down. That on the circle, Vr is equal to 0. Why do I say as expected? Why should I expect that Vr be 0 on the circle? Because remember, it's a streamline. That's probably a good answer. It's a streamline, and the velocity on the streamline has to follow the streamline. So as I go around my circle, right, there shouldn't be a v sub r. That's in fact, remember, that represents a solid surface now. So there is no velocity going into the cylinder, no fluid going into the cylinder or out of the cylinder. So that's as expected equal to 0. And the v sub theta, as I said, is minus 2 u naught sine theta. So that's the velocity on that streamline that goes around the circle. And I call it the slip velocity. Why do I call it the slip velocity? Because it doesn't satisfy the no-slip condition. So it's like I'm saying, if this is indeed representing a solid surface, and if I had viscosity, the velocity would have to be 0, because it would have to be no slip. But because we don't have viscosity in our simulation of this flow, then there is a slip velocity. Now, what is the value of the slip velocity at the stagnation point? At either stagnation point? 0, because that's a stagnation point. So it's like the fluid comes, say for example, along the x-axis, slows down, stops at the stagnation point, and then picks up velocity again as it goes around the circle. So, and what is the velocity, for example, at the highest point, when theta is 90 degrees? And what is the value? Is 2 times u naught, right? 2 times u naught. So why is the negative? The negative is because theta is measured from the, like you see here, from the x-axis. So theta is measured counterclockwise, and this velocity is clockwise. That's why there is a minus there. But interestingly enough, it reaches a maximum that is twice the free stream velocity. So when I am at the highest point, the velocity is 2 times that of the free stream. It's like the fluid has to speed up as it goes over this bump. And of course, everything that I am saying is true also for the lower side, because this is symmetric. So I'm just looking at the top side, but if I look at the bottom side, I get the same thing. So the velocity reaches a maximum which is twice the free stream velocity at the top of the cylinder and at the bottom of the cylinder. And then what happens from then on? It slows down again back to 0 to reach the rear stagnation point. So much we find by looking at the stream function and the velocity components. And of course, we could draw the entire flow field, and I'll do it at some point later. But the next thing that we should think about, and we didn't really go into the details of this for the half body, but I'll do it here, is let's find out what the pressure is on the surface of the cylinder. Because that will have an important effect for me. For example, I want to find out if there is any drag or even any lift on the cylinder. Then let's just find the pressure all along the surface. How can I find the pressure all along the surface? Bernoulli's equation? Can I use Bernoulli's equation? You were asking me. Can I use Bernoulli's equation? Yeah, we can use Bernoulli's equation. All the conditions to use Bernoulli's equation are met. So let's do that. Let's use Bernoulli's equation, B, to get the pressure. So here is the Bernoulli equation. I'm picking 2 points to write this Bernoulli equation. One is ahead of the cylinder, way ahead, sufficiently far ahead. I put it here on this figure, that dot right there. You see that? Yeah. So put that dot there. That's my first point. And the second point will be any point on the surface. So here's my Bernoulli equation. What have I neglected? The hydrostatic term, the height term. I have neglected that because it's common to neglect it in a problem like this. The contribution from the hydrostatic term will typically not be very significant unless you're dealing with a gigantic cylinder, that there is a very large difference in height. So I've neglected that. So therefore, I only have the pressure component and the velocity component in the Bernoulli equation. So way ahead of the cylinder, where I call the conditions subscript naught, that's P naught, that's the pressure of the fluid ahead of the cylinder, 1/2 rho U naught square. And then my second point is on the surface of the cylinder. I call it P sub S on the surface, and plus 1/2 rho V theta, because remember there is no VR, there's only V theta. So V theta sub S squared. And what I will do next is simply take the expression that I got. If I lower this a little bit, my V theta from up here, right, take that and plug it in my Bernoulli equation. So I'll take V theta equals minus 2 U naught sine theta squared, so it'll become 4 U naught squared sine squared theta, and put it in there. Left-hand side remains the same, P sub S remains the same, and here I have inserted the 4 U naught squared sine theta squared. Clean it up a little bit and solve for PS. Right? So solve for PS, move PS to one side, leave everything on the other side, and here is what I was after. I wanted the pressure on the surface of the cylinder, and now I have it as a function of theta. So I can find what the pressure is anywhere on the surface of the cylinder. Suppose that I want to find the pressure at any of the 2 stagnation points. Why do I plug in for theta? 0 or pi. If I put 0 or pi, that gives me 0 here. So this term disappears, and of course, I am not surprised at all that I find that at the stagnation points, the pressure will be the stagnation pressure that we learned about when we were looking at the Bernoulli equation. So it'll be P naught plus 1/2 rho U naught squared at the stagnation points. But what will it be at the top? For example, if we go back, move this down, what will the pressure be, say, on the very top? Shrink this a little bit so we can see both the top and the bottom. What is theta up there? Pi over 2. So this is 1. So it's 1 minus 4 is minus 3. Right? So I get P naught minus 3/2 rho U naught squared. Right? That would be at the top and bottom. What's significant about that pressure at the top and bottom? Is the lowest of the pressures, and what else? Is P naught minus, is even lower than the static pressure of the fluid, right? It's even less than that. Are we surprised that it's less than that? No, why not? because the velocity is actually twice. The velocity up here is twice u naught. So the pressure has to be below the static pressure. So the pressure is the highest at the stagnation point, drops to a low value, at a minimum value, at the top and bottom, and then what happens from that point on with the pressure? It increases again. Right? Because in fact, the fact that we're squaring the sine of theta makes it symmetric in that sense. So let's say that I want to plot this. Plot this pressure distribution that I just found. And a good way to plot it is to make a plot like this. And let's enlarge it a little bit. All right. That's my pressure distribution. So there is my cylinder. The red is the pressure on the cylinder that I was just talking about. So at the front, at the stagnation point, it is P naught plus 1/2 rho u naught squared. Same thing for the back. I didn't write it here, but at the back, this is symmetric with respect to the y-axis. So at the very back is also P naught plus 1/2 rho u naught squared. And then it decreases. The blue line that I put here, which is a semicircle, represents what? The static pressure of the free stream, right? That's P naught. P naught is the same all around, of course. I put it there just for comparison, so that we can see that the pressure at the stagnation points is higher than the atmospheric pressure, the pressure ahead. And in fact, the pressure drops under. That's what we were just talking about. It's the minus 3/2 as it drops on the top. And this is symmetric also with respect to the x-axis. So this pressure distribution has symmetry with respect to both the x-axis and the y-axis, which gives me a hint as to what the force will be. I get a hint out of that distribution. It is symmetric with respect to both the x and y axis. What hint do I get from that?
Constant velocity?
No, about the force. What will the net force be on this cylinder? It'll be 0. Because if I just look at the pressure distribution, it is symmetric with respect to the y-axis, which means that there'll be no force, no net force in the horizontal direction. No net force in the horizontal direction. And if I look at the fact that this is symmetric with respect to the x-axis, it tells me that there'll be no force also in the y direction, in the vertical direction. And I can show that if I actually go through the rather tedious process of finding those forces, the f sub x and the f of y. What I would have to do is, of course, I have to integrate it. I cannot just say pressure times area, because the pressure varies, but I have to integrate the pressure over the area. Okay, I'm just showing you here what the integrals look like if you were to do the integration to find the pressure. P at the surface cosine theta times A d theta integrated from 0 to pi gives you the horizontal force, and the integral from 0 to pi of Ps sine theta A d theta gives you the vertical force. And indeed, if you carry out the integration, which, like I said, it's a little tedious, not too difficult, you get 0 for both. You get 0 for s of x and 0 for s of y, which of course I'm calling them f sub d and f sub l, because if there were an f sub x, it would be called a drag, right? So there would be a drag. And the f sub y, I'm calling it f sub l, because if there were an f sub y, it would be a lift. It would be normal by definition. A force normal to the free stream velocity is a lift. So we find that there is no drag, there is no lift. You may have heard in the past that the fact that there is no drag is what is known in fluid mechanics as D'Alembert's paradox. The fact that you do all this calculation and you find that there is no drag. All right? Does anybody have a question? So let's say that I write all of the streamlines, because we were just concentrating on the surface of the cylinder. But if you write all of the streamlines, then they would look something like that. Of course, I have removed the ones from inside the cylinder. I don't really need to look at those. I could keep the streamlines inside the cylinder, but since they don't have any meaning to me in the context of looking at the flow around a cylinder, I have removed them. So what I have is I have put the streamlines that are outside. Initially we had only plotted the x-axis and the circle, but if you do everything else, that's what you get. So indeed then, combining a doublet and a uniform flow produces what we know as the steady flow past a circular cylinder. So as opposed to what we had when we looked at just the doublet, let's put these two together. Right, that was the doublet all by itself at the top. Right? It was the unsteady flow with the cylinder moving from right to left. When I add the uniform flow, then essentially I stop the cylinder in one place. So this cylinder is now not moving from here, it's right there. That's why this is steady. So this is the unsteady version of the flow field. This is the steady version of the flow field. So we call it the cylinder in uniform flow. So we saw there is no drag, we saw there is no lift. And it made perfect sense that there wasn't either when we saw the pressure distribution. Because of the symmetry of that pressure distribution, there is no drag or lift. Well, there is a way to produce a lift on this. How do you think I can produce a lift in this flow field? Huh? Move the cylinder up and down? No, I heard it back there. Who said it? You're always answering my questions from back there. Adam, are you looking? No. He said correctly, add a vortex. That might seem, wow, surprising. Remember, this is a doublet and a uniform flow. And suppose that I now say, I'm going to add to that picture, I'm going to add a clockwise vortex. What is going to happen if I add a clockwise vortex? Right? Well, we go through the first type of analysis. First, let's just try to figure out qualitatively what will happen to the streamlines if I add a vortex in the clockwise direction. So it's a negative vortex, but because usually you define them in the positive direction. So the first question is to look for what? Same thing we did for the half body and the cylinder. What's the first thing we did? Stagnation. Look for stagnation points. We already know that there are two stagnation points here when I don't have the vortex. There's the stagnation point in the front and the stagnation point in the back. So the first question we should ask ourselves is, well, what's going to happen with those stagnation points when I add the vortex? What do you think will happen?
They'll be underneath the shape.
Why?
Because your vortex streamlines going underneath it are opposing direction of the uniform flow.
Correct. So in fact, I drew here in brown the cylinder, because when I add this vortex, I'm only concerned with what's going on outside the cylinder. I could also have drawn additional blue circles inside, but I don't care about those. So I just look at the one on the surface, and like he said, I'm now adding a velocity in the clockwise direction on the surface of the cylinder. So what is that going to do? Is obviously going to move this stagnation point down, and it's going to move this stagnation point down. Because now the velocity at the points where we had the stagnation points is no longer 0 because now there is a component of velocity going up this way at this point, right? And going down this way at this point. So the point where they cancel, the 2 points where they cancel will move. So if you do it, the picture will look like this. So once you add that vortex to this cylinder, then you get this. You get the stagnation points get shifted down, like you see there. In fact, what happens if I start the vortex with a very, very small strength, very little strength, then I just move the stagnation points a little bit. If I increase the strength of the vortex, then I move the stagnation points farther down. Obviously, if I keep on increasing the strength of this vortex, what's going to happen to these 2 stagnation points?
Meet 1 point.
They'll meet at 1 point where? At the very bottom, right? So if I have the right strength, and I can calculate what the right strength would be, the stagnation point would be only 1, and it would be down here. And what happens if I keep on increasing the vortex strength beyond that?
It will just be moving up.
Where is the stagnation point going to go? It'll actually move off the surface of the sphere. Right? It'll move off. It won't be, the stagnation point will be in the flow field, not on the surface. But the interesting case is one like this, for example, where I have moved the 2 stagnation points down, but not all the way to the bottom. So what is this going to do to the pressure? Let me bring the pressure field back. This was the pressure distribution before we added the vortex, right? And the pressure distribution after. Let's think about the symmetry. First of all, symmetry with respect to the y-axis. Is there symmetry or not? So will there be a drag? I'm asking about the drag. Is there going to be a drag? No, because this distribution will change, but it'll still be symmetric with respect to the y-axis. So whatever happens on the front is exactly opposed to what happens on the back, and there is no drag. But what about the other symmetry with respect to the x-axis? That will be broken, clearly. The pressure distribution is no longer going to be the same on the top side as it is on the bottom side. So there will be a lift. There'll be a lift. So the implication then, of course, is that in order for you to add lift to this problem, you need to have a vortex. And having a vortex brings what in? The flow. No, not turbulence. We're not talking about turbulence at all. What happens, remember when we looked at the vortex, there was a new concept that came in at that point. Huh? No. Circulation, right? What a vortex does is it brings circulation, right? Because of course a vortex is the primary example of circulation. Is the fluid is just going around a loop. So that's precisely what is going on here. When we add circulation, the addition of circulation is what produces the lift. No circulation, no lift. So therefore, instead of looking at a cylinder, if we were looking at an airfoil, where you really want to have the lift, then you need to have circulation. So when an airfoil is designed, it is designed so that it produces circulation, because if there is no circulation, there will be no lift. Right? So doublet plus uniform flow plus a clockwise vortex breaks away the symmetry with respect to the x-axis and produces a lift. So now those of you who are aerospace engineering majors will look at this again in another fluids course later. Not 130B, but the ones you see after that, if you're an aerospace major. How many of you are aerospace majors? So You will see more because then you start looking at actual airfoils, and you'll remember this, hopefully, and you'll use it there. Okay, anybody has a question? Yes?
So if you introduce a uniform flow to like an unsteady flow, does it make it steady?
Not necessarily. Not necessarily. It happened in this case because it happened to be the unsteady flow for a cylinder moving. So when we added the uniform flow, we made it steady. But that's not you cannot generalize that. Adding the uniform flow will just make any flow steady. It depends on what the unsteady flow that you start with is. Any other questions? Nope. You sure? Okay, so we'll end it here. We'll end it early. And have a good Thanksgiving, and I'll see some of you this afternoon.